See, now is take an example and then evaluate the displacement gradient. We have seen displacement field, we now evaluate displacement gradient for this 2 dimensional example. Okay. This example is from the solid mechanics book by Kazemi. So, you have a plate and then the coordinates are shown before deformation and after deformation, okay, before applying the force, after applying the force, or initial state, final state. Figure shows the coordinates of rectangular plate ABCD to be 0 0 and then 0 100 and then 150 100 and then 150 0, okay, in the undeformed state. In the deformed state, the new coordinates are shown -1 and then 1 1 0 3 and then 150 to 99 and then 150 -5. Okay. We are asked to calculate the displacement gradients because 2D will have gradients. Okay. Let us see how do we calculate. Now, let us start with the definition of the displacement gradient, which I have seen in few slides ago. Few slides back we have seen the definition of displacement gradient. We said difference in displacement of 2 adjacent particles, okay, and then distance between the same particles. Now, earlier we considered only one direction. So, there was no mention of direction at all. It is understood we are working in x direction only, but now the 2 particles which we consider can be along x direction, can be along y direction, and for particle considered along x and y direction, you can find difference in displacement along x direction and y direction, and that is what is shown here. So, the denominator tells the direction along which you are going to consider 2 particles. For example, let us say x direction, let us say we consider the particles B and C. If you consider B and C, for these 2 particles I can find out difference in their x displacement and y displacement, okay. That gives 2 possibilities for the numerator. Now, we can consider 2 particles along y direction, for example, C and then D, and considering these 2 particles I can calculate the difference in displacement along x and y direction. Once again you get another 2 set values. So, finally, we have 4 combinations of displacement gradient, 2 for the direction along which you are considering the particles, 2 for the direction of displacement. Okay. So, let us write here particles along x direction, for them difference in x displacement, particles along x direction once again, but now difference in y displacement. Similarly, particles along y direction, difference in x displacement, particles along y direction once again, but difference in y displacement. Okay. So, numerator x and y direction, denominator x and y direction. So, you can calculate 4 displacement gradients. Okay. Let us do that now. Okay. Now, we will first consider particles along the x axis. In the present case, we are going to consider particles B and C. Okay. So, particles along x direction. Now, if you consider and then first we are going to consider difference in x displacement. Okay. How do you write formally? Because particles are along x direction, the denominator is delta x, and for those particles we are going to consider difference in x displacement. So, delta u x. Remember, u x tells displacement of a particle. We are going to consider 2 particles and look at the difference between them, that is why it says delta u x, and divide by delta x. Okay. Let us consider particles C and then B, which are along the x axis. Now, what is the, it says difference in displacement, which means that displacement of particle C, x displacement of particle C minus x displacement of particle B, and of course, difference in their x coordinates. Now, let us take particle C, x displacement is nothing but the difference in x coordinate. the final x coordinate is 152, initial x coordinate is 150. So, the displacement of particle C is 2 units. Now, let us come to particle B. The final x coordinate is 1, initial x coordinate is 0. So, the x displacement of particle B is 1 unit. So, the numerator is 2 minus 1 1, because we are looking at difference in x displacement. Okay. So, C has got displaced by 2 units, B has got displaced by 1 unit. So, difference in displacement is 1 unit. Okay. What is the denominator? The x distance, we are considering particles B and C, the distance between them is 150. So, this gives one of the displacement gradients 1 by 150. Now, we are consider the same particles along x direction, but now look at the difference in y displacement. When I say y displacement, it is change in y coordinate. So, how do I write delta u y by delta x, because they are particles along x axis, but now we are going to consider the difference in y displacement. Okay. So, which means that y displacement of particle C minus y displacement of particle B, and remember this once again difference in the x coordinate only. Now, let us look at particle C. Now, the y coordinate has moved from 100 to 99. So, the y displacement of particle C is minus 1, 100 has become 99. Look at particle B, 100 has become 103. So, the y displacement is 3 units, 103 minus 100, and you have that 3 here. Of course, we are looking at difference in displacement. So, that is why a minus sign here. So, minus 1 minus in plus 3 gives you minus 4, denominator is once again 150, same particles are considered along the x axis, the distance between them is 150. So, we have considered 2 particles along x axis B and C, looked at their difference in displacement along x axis gives you this, difference in their y displacement gives you this as a numerator, denominator is 150. Okay. Now, just we will repeat this by taking 2 particles along the y axis. We are going to consider particle C and particle D. So, particles along the y direction, first we will consider difference in their x displacement. How do you represent formally? Because we are considering particles along y direction, the denominator is delta y. Numerator, we are finding out difference in x displacement first. So, delta u x, which means that x displacement of C minus x displacement of D divided by the vertical distance between them, y c minus y d. Okay. Now, let us look at point C. Now, we should focus on the, for this case we should focus on the x displacement. So, 152 minus 150, that we have already seen, displaced in the x direction by 2 units. So, this is 2. Now, coming to point D, look at the x displacement, originally at 150, finally also at 150. So, no x displacement at all for point D, it is just at the same point, it has moved along the y direction, along the x direction there is no movement. So, the x displacement is 0. So, 2 minus 0 is 2. What is the denominator? The vertical distance between the 2 particles, which is 100. So, it is 2 by 100. Now, the last combination, considering the same particles along y direction and looking at the difference in the y displacement. So, how do you represent formally? Delta u y by delta y. So, y displacement of C minus y displacement of D divided by, of course, y c minus y d. Now, let us consider particle C. What is the y displacement of C? Initial y coordinate is 100, final y coordinate is 99. So, the y displacement is minus 1. Now, let us come to point D. Initial y coordinate is 0, final y coordinate is minus 5, and the displacement in the y direction is minus 5 minus 0. So, it is minus 5, final y coordinate minus initial y coordinate, that gives you the y displacement. What is the difference in displacement between C and D? Minus 1 minus of minus 5 gives you 4. The denominator is, of course, the vertical distance between them, which is 100. So, we got now 4 values of displacement gradient. Let us arrange them. Okay. How do we arrange them? the way in which I have arranged is, first we consider particles along the x axis which were C and B, that is denoted by CB here. We calculated two gradients for them, the denominator is delta x here, delta x here, numerator depends on which displacement we are considering, x displacement, y displacement. Then we consider particles along the y axis C and D, that is why the denominator is delta y. Now we considered x displacement and then y displacement. So now I have taken those values, arranged column wise. Why specifically column wise we will understand later. Right now I have taken all the numerical values from the previous slides and then filled up here. Okay. So now what is that we have seen? We have seen a displacement field in 2D and then also discussed displacement gradients for 2D because of two directions along which I can consider particles, two directions along which I can consider displacements, 4 displacement gradients can be found out, and that is what we have done now. Okay, now let us move to 3-dimensional case. Okay. A very good representation, a very good example from stress and strain. Note the axis characteristic of that book, the x axis here, the y axis here, the z axis here. Okay. Now the initial configuration, the undeformed state is a cube, You applied a force and it has become a cuboid like this. Okay. So what has happened? Along the x direction the length has decreased, along the x direction original length, this was the original length, the length has decreased. Along the y direction the original length was this much, the final length is become twice of that. Along the z direction no change at all, Okay. So the cube has become cuboid with decrease in length along x axis, increase in length along y axis, that is what has happened. Now what is shown on the right hand side is this view, you are viewing from this direction, that is why you have x axis here and then the y axis here. Okay. Now what are the things shown here in this diagram? Let us go one by one. The initial position of A, B, C, D are shown in the initial configuration. Now the same A, B, C, D are shown in the final configuration also as A dash, A was here and A dash is here, it has a vertical displacement. So this is A dash, this arrow mark represents the displacement, direction of displacement, A is here and A dash is here. Okay. Now let us come to B, B is here and B dash is here. So it has moved in this direction and this arrow mark represents the direction, B is the original position and B dash, this point is B dash, that is the final position. Now C has not changed at all, C and C dash are same, so C and C dash are same. Now let us go to D, D was originally here and it moved along this direction and this is D dash, that is what is shown here. This arrow mark shows that D has moved along the x axis, of course along the negative x axis by half a unit. Okay. Okay. So this is D dash. Now what else is shown? Below the new position 3 values are shown. Okay. What are they? They represent displacement of these A, B, C, D particles along x, y, z direction. Earlier we have gradually moved from x to x and y, now to x, y, z. So the numbers below the new coordinates represent the displacement of the particles A, B, C, D, because it can happen in 3 directions, 3 values are given. So let us take the case of A. A was here, it has moved to here, which means that there is only vertical displacement along the y direction by 1 unit. So you have value of 1 here, no displacement along x direction, no displacement along z direction. So it is indicated as 0, 1, 0. Now let us take B. B has moved from here to here, but in terms of coordinate along coordinate direction it has moved by half a unit along negative along the negative direction along x axis and 1 unit along positive y axis. So, that is why you have minus half here, 1 here, and of course, no movement along, no displacement along z direction, hence it is 0 here. Now, coming to C dash, no movement at all. So, displacement z is 0 along all the 3 directions. Coming to D dash, it has moved by half a unit in the negative x direction, and there is in this direction there is no movement along y axis, z axis, and that is why minus half, 0 and then 0. Okay. So, we have shown a 3 dimensional geometry, initial configuration, final configuration. We have shown one view of that, the particle showing A, B, C, D, initial position, final position, arrow marks going from initial to final position, and the displacements of the particles as well. Okay. Now, with all this information, we will find out the displacement gradient. Before that, how do we represent displacement field in 3 dimensional case? U has x component, y component, z component, and all of them can be functions of x, y z, x y z, x y z, of course, vectorially written as I, j and then k. Analogous to our velocity field, okay, we write v as v equal to v x, v y, v z. Similarly, here we have written u vector in terms of u x, u y, u z. The displacement in the x y z, that x y z directions can be function of x y z, okay, and that is what we have seen here as well. The displacements, whatever numbers shown are can be functions of x y z. Here it may be a constant, but in general they are functions of x y z. Okay. Okay, now we will have to find out the displacement gradient. Okay. So, how many entries do we expect? 9 entries we expect. Okay. 3 directions along which we can consider the particles, and for every direction I can consider their x displacement, y displacement, z displacement, difference in their x, y, z displacements. Okay. So, let us take first particles along x direction, which means I am considering particles A and B, A and B. Okay. Now, having considered particles along A and B, I am going to consider their difference in x displacement, y displacement and z displacement. Okay. So, if you look at the denominator, it is always delta x, because we are considering particles along x axis. Numerator, difference in their x displacement, y displacement, z displacement. Okay. Now, how do you write difference in x displacement? Because we are considering particles A and B, x displacement of B minus x displacement of A divided by the x b minus x a. For the case of y displacement of B minus y displacement of A, denominator is same, z displacement of B, z displacement of A divided by x b minus x a. Now, remember we said these numbers represent the displacement of the particles along the respective directions, x, y, z directions, along the directions. So, to calculate to evaluate the numerator, it is enough if you look at the difference in the displacement along the respective directions. For the x direction, minus half minus 0, that is what you see here, minus half minus 0. What is the denominator? Because we are using small x, it is a distance in the final configuration, and what is x b minus x a? It is in the final configuration, the x distance between b dash and a dash is half a unit. So, half minus 0, difference in the x coordinate, this gives you a value of minus 1. Okay, just let me repeat, considering particles A and B, for the first entry we are looking at the difference in x displacement, and the 3 numbers here below the final coordinate tells you the displacement of the particles. We will have to look at the difference in displacement, that is all is required. For the first entry we will have to look at the difference in x displacement. So, minus half minus 0 divided by the distance between particles A and B along the x axis, because we are using small x, it is in the final configuration. So, it is half minus 0 giving you minus 1. Okay. Rest becomes very simple. Now, if you take displacement along difference in displacement along y axis, it is for B dash also it is 1 and A dash also it is 1. So, 1 minus 1, so it is 0, denominator is same, of course does not matter anyway. And what about displacement in the z direction? It is 0 for both of them, and so 0 minus 0, and denominator is still of course half minus 0 giving you 0. So, these are the entries minus 1, 0 and 0 corresponding to particles along x axis. Okay. So, let us complete the matrix. Now, there will be 9 entries, each column corresponds to the direction in which we are considering particles, okay, and each row corresponds to the direction of displacement. So, as we have done earlier, for particles along one direction, we filled up along one column. Okay, look at this delta x, delta x, delta x, numerator is delta ux, delta uy, delta uz. Okay. So, all of them have been put in one column. So, if you consider particles along y axis, you will get these entries. If you get particles along z axis, you will get these entries. Now, I filled up these entries 1, minus 1, 0 and then 0. If you consider particles along y axis, you will get these entries. If you consider along z axis, you will get these entries. Okay. So, if you consider particles along y axis, let us say c and then a, and the final distance between c and a is 2. So, all the denominators are 2, then 2 and then 2. What about numerator? You should consider difference in x, y, z displacements. If you consider c and a, the difference in x displacement is 0. So, 0 by 2. If you consider the difference in y displacement, it is 1 minus 0. So, you have 1 here. Difference in z displacement is of course 0. So, that is why you have 0 here, 1 by 2 here, 0 here. Similarly, of course, in the z direction there is no displacement at all. So, all values are 0 here. So, now we have filled up all the 9 entries. It was very obvious that in case of 3D we will have 9 combinations, and we have found out all the 9 displacement gradients. Yeah, now you would have easily sensed that we have been indicating 2 directions all the time. Any physical quantity which requires 2 directions to describe is a tensor. So, we have introduced in fact very gradually a displacement gradient tensor. Okay. So, initially because it was 1D, it looked like a partial derivative for you, dou ux by dou x. Remember earlier slides has delta ux and delta x, but they can vary locally. So, we should write in terms of partial derivative. We slowly move on to 2D, and then we wrote dou ux by dou x and then dou u by dou x for particles along x axis, and for particles along y axis it was dou ux by dou y, dou uy by dou y. Now, in the just previous slide we have moved to the 3 dimensional case, and we have got 9 entries for the displacement gradient tensor. Certainly, you would not have sensed here that it is a tensor. You would have got some clue when we moved on to 2D. Certainly, it was very clear when we discussed the 3 dimensional case that matrix is a tensor. What are the 2 directions? As I told you, one direction is for the particles along which are considering, along which direction we are considering, and one direction for the displacement. Okay. Now, just to explain this, just to understand this, of course, we know that in using the definition which we introduced earlier for displacement gradient, we said difference in displacement of 2 adjacent particles divided by the distance between the same particles. We have considered particles along x, y, z direction, that is one direction. We have considered displacement in x, y, z direction for those particles, that gives another direction. So, we have 2 directions to represent each entry in this matrix, and hence it is a displacement gradient tensor. Okay. Now, this displacement gradient tensor is similar to a gradient of a temperature. Physical significance, in terms of physical significance, what does gradient of a temperature tell you? How do you represent? First of all, temperature is a scalar. You have a gradient of a temperature. moment you take a gradient of a scalar, it becomes a vector. Why? Temperature field is there, moment you tell gradient you should attach a direction, temperature varies along x axis in this way, temperature varies along y axis in this way with some magnitude or some value minus or positive. Okay. So, that is why moment you take a gradient you attach a direction to temperature, whenever temperature field is scalar, but now I say rate of change of temperature along x axis, rate of change of temperature along y axis. So, you attach a direction, that is why you have dou t by dou x and then I, dou t by dou y j, dou t by dou z k. So, gradient of a scalar is a vector, physically why? Scalar has no direction, moment you take a gradient attach a direction, moment you attach a direction becomes a vector. Now, if you extend analogously to this displacement, what you have got is a gradient of a displacement. Displacement itself is a vector. Now, we are going to say how displacement varies along x axis, y axis, z axis. Instead of saying this how displacement varies along x axis, y axis, z axis, we said 2 particles, 2 points, etc., without saying this. Now, because we know formally, we can use a very formal statement. Let me repeat, displacement itself is a vector, we are considering gradient of displacement. So, we are attaching a direction on top of a direction, okay, which makes gradient of a vector as a tensor. Okay. The first direction, whichever is first, one direction is the direction of the displacement x, y, z direction. Second is the direction of the gradient direction in which you are interested in the variation, along which direction interested in the variation, that is second direction. Okay. First direction of the displacement, second is the direction in which interested in the variation of the displacement. So, those two directions result in a tensor. Okay. So, if you understand scalar temperature, gradient of temperature, then easy to extend to gradient of a displacement field, and that is a displacement gradient tensor. Okay. So, to summarize, we started with defining types of deformation. It could be change in length or change in angle, it could be and as well, and we quantified it by definition. We measured, we expressed change in length, change in angle in terms of normal and shear strain, okay. And then we said this normal strain, shear strain are somewhere depending on the displacement of the particles or the points. So, we have discussed displacement field and displacement gradient tensor slowly from 1D to 2D to 3D. So, next we will have to relate these two, and that is what we will discuss in the next lecture.